Welcome to this complete guide on chemical bonding. We'll be covering ionic, covalent, and metallic bonding, as well as essential exam techniques. Today we'll start with the definition of chemical bonding. Then we'll cover ionic, covalent, and metallic bonding, including their properties. Finally, we'll share some valuable exam tips. So what is chemical bonding? It's the force of attraction that holds atoms together in a compound or element. Atoms bond to achieve a full outer electron shell, which is the most stable configuration, like a noble gas. Atoms bond for stability. Most have incomplete outer shells and are reactive. By bonding, they mimic the stable electron arrangement of noble gases, typically achieving 8 outer electrons. Chapter 1 focuses on ionic bonding. This type of bonding helps metals and nonmetals achieve stability through electron transfer. Ionic bonding occurs between a metal and a nonmetal. The metal transfers electrons to the nonmetal. This gives both a full outer shell, but creates charged particles called ions. In the example of sodium chloride, the sodium atom loses its outer electron to become a positive Na ion. The chlorine atom gains it to become a negative Cl ion. The opposite charges attract, forming a strong ionic bond. Metals form positive ions or cations by losing electrons. Nonmetals form negative ions or anions by gaining electrons. In an ionic compound, the positive and negative ion charges balance out to zero. Examples of ionic bonding include sodium chloride, formed by Na and Cl ions. Magnesium oxide involves Mg² and O², both transferring 2 electrons. Calcium chloride requires 2 Cl ions to balance 1 Ca² ion. Chapter 2 is about the properties of ionic compounds. We will explore how their giant ionic lattice structure influences their physical behavior. Ionic compounds form a giant ionic lattice, a repeating 3D arrangement of alternating ions. This structure is held together by strong electrostatic forces of attraction in all directions, which gives them unique properties. Ionic compounds have high melting and boiling points due to the strong electrostatic forces. They are brittle and shatter easily when a force is applied. They only conduct electricity when molten or dissolved, as ions must be free to move. Electrical conductivity changes based on the state of the ionic compound. Solid, molten, or dissolved. Conductivity occurs because ions must be free to move, which happens when melting or dissolving the lattice. Chapter 3 introduces covalent bonding, explaining how nonmetals achieve stability by sharing electrons. Covalent bonding involves 2 nonmetal atoms sharing pairs of electrons rather than transferring them. Each shared pair is one covalent bond. Both atoms share the electrons to fill their outer shells without becoming ions. Dot and cross diagrams illustrate sharing. For hydrogen, a single covalent bond forms as each atom shares 1 electron, giving both a full shell of 2. In water, oxygen shares with 2 hydrogen atoms through 2 single bonds. Common covalent molecules include water, H2O, with 2 single OH bonds, and ammonia nitrogen trihydride with 3 single NH bonds. Carbon dioxide has 2 double bonds. Methane, carbon tetrahydride, forms 4 single CH bonds. Chapter 4 explores the properties of covalent substances and why simple molecular substances behave very differently from ionic compounds. Most covalent compounds are simple molecules. They are small, discrete groups of atoms held by strong covalent bonds. The forces between these molecules are very weak. These weak intermolecular forces are what break during melting or boiling, not the strong covalent bonds. Simple molecular substances have low melting and boiling points because little energy is needed to break the weak intermolecular forces. They do not conduct electricity as they have no free electrons or ions. Many are soluble in water, depending on their polarity. It's vital to distinguish between strong covalent bonds, which hold atoms within a molecule and are not broken during a state change, and weak intermolecular forces, which act between molecules and are easily broken during melting or boiling. Chapter 5 focuses on metallic bonding, the unique structure that explains the useful properties of metals. Metallic bonding occurs in pure metals and alloys. Metal atoms release outer electrons into a sea of delocalized electrons. The positive metal ions form a regular lattice held together by the attraction to this electron sea. The metallic structure consists of positive metal ions in a regular lattice. The delocalized electrons move freely as an electron sea. Strong electrostatic attraction between these opposite charges holds the structure together. The structure involves 3 key elements: a positive ion lattice, a sea of delocalized electrons free to move, and the strong electrostatic attraction between them that maintains the integrity of the whole structure. Chapter 6 covers the properties of metals and explains how the metallic structure accounts for their characteristic physical behavior. Metals conduct electricity because the delocalized electrons are free to move. When a voltage is applied, they drift in one direction, carrying the charge. This is the key reason metals are excellent conductors. Metals are malleable, hammered into sheets, and ductile, drawn into wires. When force is applied, the ion layers slide over each other. The electron sea keeps the bonding intact, preventing shattering, unlike ionic compounds. In summary, metals conduct electricity and heat due to delocalized electrons. They are malleable and ductile because ion layers can slide without breaking bonds. They also have high melting points due to strong electrostatic attraction. Chapter 7 concludes this video by comparing all three bond types, ionic, covalent, and metallic, side by side. This table compares the particles involved, what forms, melting points, and conductivity for ionic, simple covalent, and metallic substances. This visual comparison summarizes the three bond types. Ionic transfer electrons, covalent share electrons, and metallic involves a sea of delocalized electrons. Melting points vary greatly. Ionic and metallic substances generally have high melting points due to strong bonding. Simple covalent molecules have much lower melting points because only weak intermolecular forces are broken. Ionic compounds only conduct when molten or dissolved, as ions must be free to move. Covalent substances never conduct. Metals conduct electricity in all states because of their constantly available free electrons. Ionic compounds are brittle because shifting layers align like charges, causing repulsion and shattering. Metals are malleable because the sea of electrons adjusts when layers slide, maintaining the bond and preventing breakage. This final chapter provides exam tips to help you maximize your marks on bonding questions. The golden rule is to always link bonding to properties. Don't just name a property. Use the correct scientific terms to explain why it occurs based on the substance's structure and bonding. To structure your exam answers, first state the type of bonding or structure, then describe what the structure contains, and finally, explain the property using that structure. Avoid common exam traps like saying covalent bonds break when a substance melts, or ionic compounds always conduct electricity. Use correct terminology like intermolecular forces and free, delocalized electrons. Use key vocabulary like electrostatic attraction, delocalized electrons, and intermolecular forces. Pay attention to command words like explain, describe, and compare to ensure you answer fully. Test your knowledge with these quick-fire practice questions. Remember to use the three-step structure: name bonding, describe structure, and explain the property. To summarize, bonding involves a transfer, sharing, or delocalization of electrons, which determines the structure and ultimately the properties of the resulting substance. Remember these key takeaways. Atoms bond for a full outer shell. Bond type depends on the elements. Structure determines properties, and always explain the why in your exams.